what we had was a phone call at 3 in the morning. Anna, I observed the wrong star. And I said, you better not. There is a European line in the spectrum. Oh, I was like, send me the data at 2 in the morning. That was fun. And so I made a joke. It's like, Alex, my former student, is like, Alex, I think you found the first R-process galaxy. Because we had never found an R-process enhanced star in a small dwarf galaxy, ever. We had no expectation to find one either. And then he found 7.
That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering. Thousands of confident religions, ideologies, and economic doctrine. Every hunter and forager, every hero and coward, every creator and destroyer of civilization. Every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they can become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of the space on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds, our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. There is perhaps no better demonstration of the folly of human conceits than this distant image. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Thank you all for coming. We are the Secular Society of MIT, and we welcome you to our second Sagan Day celebration. How many of you were here in the last year's Sagan Day celebration? Okay. By the way, a show of hands, how many of you got the Lovecraft reference in the name of the event? Okay, a couple of you. That's actually a reference from the Cthulhu mythos of H.P. Lovecraft. But anyway, reference jokes aside, I'm Sohan D'Souza, I'm the president of the society, and thanks for coming to our event. Hope you're enjoying the pie and the Bacon of Cosmo or something resembling it. And we are very privileged today to have with us and speaking at the Sagan Day event, Dr. Anna Frebel. She's a Silverman 1968 Family Career Development Associate Professor of Physics at the MIT Physics Department. Her research interests broadly cover the chemical and physical conditions of the early universe and how spectroscopic analyses of the most metal-deficient stars can be employed to understand the early universe. She expanded her work to include developing a more comprehensive view of how the Milky Way were formed. Dr. Frebel was awarded, among many awards, 2007 Charlie Heisler Prize, 2010 Annie Jump Cannon Award, and 2013 NSF, that's National Science Foundation Career Award, among others. She previously held a Clay postdoctoral fellowship at the Harvard Smithsonian Center for Astrophysics from early 2009, and in early 2012, we were incredibly lucky to have her join the MIT Physics faculty, and she is now a tenured associate professor of physics here. Please welcome Dr. Anna Frebel.
Hi everyone. We'll just do a quick shuffle here. As you can see, you are in a very lucky position because you're getting 1.5 of me. Anna. He's currently also trying to escape through my belly button, and I hope we can all agree that that's not the great way to go. So once in a while, you know, it kind of hurts. So if it gets too bad, I will sit down, but right now I'm behaving. All right. So. Do you have a laser pointer?
Oh,
or some sticks or something? So for more than 10 years, I've been searching for the oldest stars, and I will tell you a little story that relates to that today. So I will give you quite some background material first, and then I figured that you'd like a slightly more chunky presentation and not the total vanilla version, but I promise I will explain everything and you're welcome to interrupt me. That's no problem. So today I wanted to talk to you specifically about a rare and prolific nucleosynthesis event, so an element creation event that occurred a long time ago in a small dwarf galaxy. But we'll actually only get to this at the very end. We need to put together a whole bunch of separate pieces, and in the end it will all come together. So that's the story for this evening. Now the story starts about 14 billion years ago with the Big Bang. And the Big Bang left behind a universe that we call pristine. It was just made from hydrogen and helium. Tiny little bit of sprinkling of lithium, but we're not going to worry about that. From this pristine material here, the very first stars formed. Now, as it turns out, it's actually quite difficult to make stars from just hydrogen and helium gas, because hydrogen and helium are pretty simple atoms, so they don't have enough. They don't have many options to wiggle around and have many transitions to radiate away energy. As a consequence, the very first stars are very massive, something like of order 100 solar masses, because the gas just couldn't clump enough and cool enough to form smaller fragments that then would turn into smaller stars. However, that did work for the next generation of stars and onward until today, because what happened? These stars, because they were really massive, they exploded after just a few million years. That's really, really short on cosmic timescales. And of course, they forged elements in their cores for energy generation purposes, and I'll talk a little bit more about that in a moment. And so when they exploded, all these new elements came out and got spilled into the surrounding gas. And that meant there suddenly were more complex elements, atoms, in the gas, and they did their thing. They provided cooling to the gas, and so the next generation that formed from this enriched gas now included also small stars, the mass of the sun and less. And the cool thing about those is that the sun has a lifetime of 10 billion years. A star that has even less mass has even longer lifetimes. So stars, those are particularly interesting to me, that have about 0.6 to 0.8 solar masses. They have lifespans of 15 to 20 billion years, which means if you form a low mass star at this early time here, and we are talking, this is millions of years, so they formed some few 100 million years after the Big Bang, and these ones formed within the first billion year. So if you form them here, they are still alive and kicking today, right? So we can still observe them, find them, and then observe them. The finding is the tricky part, but that's what I've been doing for a long time, basically. Okay? And the cool thing is that, and I will go into much more detail on that topic, is that they, because they're formed from the gas enriched from the first stars, they encode, they preserve the signature, the chemical signature of all this junk that came out of the first stars. Or, more broadly speaking, of all the generations that have preceded the star before it was born, right? Everything that contributed to the enrichment, the chemical enrichment of the gas cloud from which these stars formed. So that's the big picture. To fine-tune this just a little, if you again think that this is the primordial, the pristine universe after the Big Bang, here we have the first stars. They evolve, explode as supernovae, and all the elements created are given back to the reservoir. And so with every cycle here, the universe gets enriched just a little bit more in all the elements. Really, basically all the elements were there from day one, and then with time it was just more and more and more and more, right? It's not that on day one you had hydrogen, on day two you had helium, on day three you had lithium, and on day 92 you have uranium. That's not the case, really. Pretty much everything was there from day one, and then it's just a constant build-up. And we make use of this fact because the consequence is that early stars contain very little of everything, and the younger stars, like the sun, contain a larger amount. Now, what is large? Large is actually not so large, but it's larger. Let me remind you first that certainly the early stars have chemical hydrogen helium composition close to 75 to 25%, which is the primordial pristine composition. And that actually hardly ever changes with time because the amount of elements is very small. But actually, before I give you the numbers, so as I said, we make use of this fact because we can actually not really age date all stars or any stars. It's really difficult. But we can look for the stars that have the least amounts of hydrogen, of elements heavier than hydrogen and helium in them, because it implies that they must have formed at a time when this cycle here had only gone round a few times. Because you can't take elements away from the universe. Once they're there, they're there. You can, once in a while, you lock up some in a white dwarf or throw some in a black hole, but in terms of the mass, it's nothing. So it doesn't really work. There's no ginormous vacuum cleaner that can take this away. So the consequence is then that so the sun is 4.6 billion years old, which means it formed after 8 billion years of enrichment by massive stars and actually a whole bunch of other things we're not going to go into today. And in those 8 billion years, the universe has produced 1.4% of elements heavier than hydrogen and helium from hydrogen and helium. Okay? Today, this number has already grown to about 2%, which also means, in this kind of exponentially increasing function, that in some number of billion years, this number is going to go way up, and things will dramatically change because I'm not entirely sure how to make stars from gas that's half iron or carbon, but we shall see, or whoever was at that time will see. But so nothing we need to worry about right now. But I think it's an interesting thing to think about. So the stars that we are looking for, the oldest stars, have comparatively little, so 10 to the minus 4 to 10 to the minus 7% of heavy elements. So you can almost count the kilograms that they have. Again, because they formed from gas that was possibly enriched by only one previous supernova, or maybe 2 or 3, and that material is of course spread over large amounts of gas, and so there's really not that much left in the stars. All right, so I'm a stellar spectroscopist. I already said we are looking for the chemical abundances, and we're actually looking to find basically hardly anything of them, because that tells us that they are very early, or formed very early on. And so this is here depicted in spectra. This is the spectrum of the sun. It looks pretty noisy, but actually this is not noise. These are all elemental lines that are just overlapping because the abundance of the elements is so high, right? And we have this nomenclature here as a logarithmic scale. We use iron as a measure for the overall heavy element content of the star. And by definition, this is set to 0 for the sun because the sun is our reference element. And then it goes, negative here, so in orders of dex basically down. Now, if we indeed dial back the clock, we go to a star that has 1.5 orders of magnitude of iron and other elements less than in the sun. You see the spectrum looks pretty cleaned up, right? You can see individual lines. They're not so blended, maybe here a little bit, but that's easy to work with. Now we dial it down another 2 orders of magnitude, or 1.5 or so, and we get to this one here, yet more cleaned up. What you see, the little wiggles here, that's no noise, right? Because these are real stars that they are faint, they're far away. Telescope time is expensive, so we have noise in the data. The sun you get for free. Actually gives you too much light. That's a different problem. And so you dial it down another 2 orders of magnitude, and you find only this, but I hope you can see this little wiggle here. So there's almost nothing left in those, right? So this is the 2nd generation star that formed from gas enriched by just one first star, to the extent that we can tell. And it's very exciting to find this little wiggle, because we can still measure something. We found cases where there's actually nothing to measure anymore. That has its own appeal, but it's of course also a bit frustrating because the upper limit is never as good as in measurement. So we're looking basically for the almost nothing. Now, one more thing that we need to introduce here, it's a jargon term. This is the periodic table. I'm sure you've seen it before. The chemists are usually interested in the columns. We're interested in the row. I'm interested in the rows, but actually most astronomers don't care at all. It's like, oh, too many elements. What's this one? ND, DB, TB, GD. It's too complicated. So a long time ago, someone really clever came up with a scheme to simplify life. Hydrogen is called X, helium is called Y, and the rest is called Z. Grouped together as metals. Okay? So, neon is a wonderful metal, wouldn't you agree? Any chemists in here? No, I'm no chemist, so, I don't care. Sorry. Which means when we search for the oldest stars, we look for the most metal-poor stars because, again, the content of the heavy elements, heavier than hydrogen and helium, with respect to the sun, this is what we're looking for, right? The smallest amounts of all this junk here together. So we call this the most metal-poor stars. So I will be talking a lot about metal-poor stars. What it should mean to you is that it's a synonym for old, or very old, or extremely old, or mega old, that kind of, you get the flavor. All right, so today's story has 3 components. We need to talk a little bit about nuclear astrophysics and how the elements are made. We need to talk about stellar archaeology, which is the concept of using old stars to extract this information about these early enrichment events, because they preserve them for billions of years. And then we talk a little bit about dwarf galaxy archaeology, and that's what's kind of pulling everything together, because we can find also clean chemical enrichment signatures in small dwarf galaxies, and that's pretty new and exciting. All right, so I'm sure most of you are familiar with the fact that you can, that in stars, for energy generation purposes, you have, or there happens nucleosynthesis. As I said before, the stars contain, or they're made mostly from hydrogen and helium. That remains true. And so helium is fused into hydrogen. Hydrogen is confused. No, I'm confused. Let's show it like this. I think that's better. So you see, through a series of steps, protons, initially 4 protons, get converted to helium nucleus, and then if you smash 3 helium nuclei together, you get a carbon. You add more carbon, you get oxygen, and so forth. And in the end, you end up with this iron atom. And here, this little graph shows you how much energy you get out. So you get the most energy out for the lightest nuclei, like protons. Smash 2 protons into each other, you get the most energy out due to the mass defect. And it gets successively harder and harder to squeeze energy out if you involve heavier and heavier nuclei in your reactions. And the end of the line is reached with iron. If you want to fuse 2 iron atoms together, it would cost energy. The star doesn't like to do that because it needs to get energy out to sustain the luminosity and to stay in equilibrium. So if you turn the engine off, what you're going to get? A catastrophe, also called supernova explosion. Right? You have an implosion actually of the core region, and there's a neutron star that forms, and that one's really hard, and so the shock waves bounce off the hard neutron star. It's like a basketball, when you bounce it, and then the shock wave goes, turns around and then disrupts the star, and we have a supernova explosion. So that happens in massive stars. The less massive stars like the sun, they will burn only maybe up to here or so, carbon and oxygen, because there's not enough mass sitting on top of the core to make it hot and dense enough to get these more difficult reactions here out that give you so little energy. All right, so, but the problem is, most of the elements in the periodic table are heavier than iron. So how are those made? Those are made mostly in neutron capture processes, and we differentiate here between 2, the slow and the rapid one. I'll explain the slow first. So you have a seed nucleus like iron, and if you add a neutron to it, it swells, and then it decays because it's radioactive. And then you add another neutron, it becomes radioactive and it decays. And so you add a few neutrons, 1, 2, 3, whatever. And so this is a chart. It's an excerpt from the charts of the nuclei. So you have neutrons in this direction and protons in that direction. So in this case here, you add a few neutrons and then it decays. You add 1 neutron, it decays. You add a few neutrons, it decays. And so it zigzags up here and eventually produces something of all the isotopes that make up all the elements heavier than iron. And that happens in advanced stellar evolutionary phases of intermediate mass stars, and it's very well understood theoretically. Let's look on this one here. Now, there is another option when you're in a hurry. You have your seed nucleus, your iron, and now within the time scale of a beta decay, which can be very short, you bombard that poor iron nucleus like hell, basically. And so what happens? You have your iron nucleus, it goes, and that's of course highly radioactive, but this neutron flux is only really short, 1, maybe 2 seconds. So that stops, and then, what's that big neutron-rich nucleus going to do? It's going to decay. And so this way you can also make all the heavy elements. All right, so have a little cartoon here as well. So started with the iron atom. It gets bombarded with the blue neutrons. There are some sort of intermediary step that happen as these neutron-rich nuclei are built up, and then in the end, you end up with something like that. Now I have a more detailed cartoon that shows that. Let's see. Good. That one sometimes takes a second to load. So same thing. This is the full charts of the nuclear. Yes.
In the previous slide, you had the chart for the energy of the fusion thing. Like, there's a peak with the lighter elements, right? Which element is that in light? Like, yeah,
This one here,
yeah.
lithium. Well, lithium is kind of special. Lithium is not made in fusion. Usually, it's made through spallation, cosmic ray spallation, or during Big Bang nucleosynthesis. So it has a special status. So it's not really created in stars. And certainly, I mean, you can't get any. I don't actually know too much about lithium here, but apparently you get energy out. But stars don't make use of that. Oh, sorry, now you have to see it all again. Yeah, Carl Sagan would have appreciated that. All right, good. So this is the full charts of the nuclei. Again, neutrons go this way. So if you bombard something with neutrons, it's going to go this way. If it decays, it goes diagonally up because neutron gets converted to a proton. Okay. So this. Now the little squares here, these are the stable isotopes. And so this is where elements ultimately decay to. And what you're going to see when I started is here they use protons as seed nuclei, but it doesn't really matter if it's a proton or an iron as a seed nucleus. It'll shoot up here all the way into the trans-Uranian region here, and then it will decay back. Now, who has heard of the gravitational wave discovery last year by LIGO? Most people. And then you probably also heard that there was an associated electromagnetic event called a kilonova. So it was not just detected by LIGO, but it was also seen by astronomers in telescopes. Now, what they saw was that many of us kind of knew for a long time is what that light, the light that they saw with the telescopes, that is the light that comes out of this procedure here. Because what happened is that the R process, the rapid neutron capture process, took place in these merging neutron stars, and I'll talk more about that. And, well, actually, maybe we'll just show it, and then you will literally see what they saw. So within, not even 1 second, all the neutron-rich isotopes are made, and then they started to decay. And when they start to decay, this is radioactive stuff. That is a lot of light that comes out. And it takes a few weeks for the majority of the elements to reach some of their stable nature. That is what the kilonova observations show. That radioactive light that came from the decay of these neutron-rich isotopes after this R process event took place, after this neutron bombardment onto whatever nuclei happened to be around. So that's pretty cool. So what they saw really was the best example of nucleosynthesis in action. We all now know that nucleosynthesis happens in the course of stars, but we'll never be able to actually see it. we're not gonna surgically insert anything into a star to take a look, right? So it's all deduced. It all makes sense, and everyone believes it to be true, but we can never see it. But in a kilonova event, you can see, you know, the direct result of these elements decaying and becoming stable. I think that's pretty nifty. All right, so I said both the slow and the rapid neutron capture processes produce isotopes that make all the heavy elements. And here in blue, this is depicted in a fairly simple way, namely in the periodic table. So all these elements are made, although not all the isotopes are made that, you know, that make up all these elements. There are many elements that contain 5, 6, 7, 8 isotopes. Okay, so the R process can't reach them all, but most of them. So there is some element production. Now, for comparison, the S process also makes all these elements, minus thorium and uranium. We can't get there. It ends at lead and bismuth here. These ones are radioactive, so I'm mostly focused here on the stable ones. Actually, these ones I should not have labeled red, but whatever. The point is here that the S process makes a slightly different set of isotopes of all these elements. But that's a you know, a detail. But you can see that if you just measure any of these elements in a star, the question is, which process was responsible for it? We can't tell. We can only measure elemental abundances in stars. We can't really measure isotopic abundances so well. We can do that for the sun because of stardust grains, but we don't have that option for stars. So we need to get a little bit more clever about this. As it turns out, the R process and the S process both have a kind of a stereotypical pattern when you look at the abundances as a set. So here's abundance and here's atomic number. Here are all the names, so you can learn them. I will ask you at the end which one is which. Little quiz. Now this pattern looks a little bit wild perhaps to you, but there's something like a first peak here and a second peak here and a third peak there. And if you stare at it long enough, you'll kind of get to know it a little bit. And as it turns out, we have found stars that show exactly this pattern. I'm going to skip that and go straight here. So in blue, you have the same pattern again. And in this case, and let me say first, in red, you have the abundance measurement that were obtained for a star that presumably formed from gas that was enriched by an R process event somehow. Now, the blue pattern here is actually that extracted for the sun and then scaled a little bit. And as you can see, it almost looks like a connection of the red dots, right? But it's not. It's just matched against the red data points. And so what we have learned from this, we have about 30 stars now that are R process enhanced. And they all match this scaled solar R process pattern. So this R process that I just showed you, it makes the same elements in the same proportions, lots of the isotopes really, every single time. Below barium, the really light ones in the first peak over here that are conveniently cut off from this floor. The story is a little bit more complicated, but above barium here, every single time it just knows what to do. There's no wiggle room. And you know, as I said, the sun is only 4.6 billion years old. Our stars are probably more like 13 billion years old. So it's it seems to be like a universal process that works no matter where and when it happens. Now, where do we find these R process old stars? We find them in the outskirts of the Milky Way. For reference, we're sitting somewhere here. and the outer parts here of the galaxy are a bit of a junkyard of the Milky Way, because the Milky Way wasn't always what it looks like today. It started 13 billion years ago as a proto-galaxy, and it happened to be a little bit bigger than its neighbors, so it ate its neighbors. That's cosmic cannibalism, and it grew from doing that. It still eats its small neighbors. The dwarf galaxies that are orbiting the Milky Way are the ones that are not eaten yet, but they will. Some already had a little chunk taken out. No, I'm not kidding. It's a hostile place out there. At least if you have a galaxy. And so we find them in the outer parts, and because of this, eating up things, the out-processed stars that we find likely formed, well, they're older than the Milky Way itself, and they're likely formed in small dwarf galaxies that have been eaten, and which means that we don't really know in what kind of systems these out-processed stars form. And as you will see later, that's a big problem. So they are just kind of like orphans collected. We don't really know where they come from. All right. So let me summarize this concept of stellar archaeology here. We find the oldest stars in the outskirts of the Milky Way. Small fraction of them are out-processed and hence stars. We study their chemical composition, and that tells us about the chemical composition of the Dwarf gas cloud from which they're formed 12, 13 billion years ago. And that tells us, and then our job is to figure out, okay, what produced the metals in these early clouds? Was it the first stars? Was it the first stars plus a few other generations? What kind of objects were those? What kind of processes occurred there? And so that's kind of the aim of the game, this big puzzle. And so actually I just want to focus on this here, that this concept here makes a really great tool for what we call near-field cosmology. So we don't need to use very distant galaxies that are usually used to explore the early universe. Their light has traveled for billions of years, so when you finally collect it with a telescope, you see them how they were when they were young, right, in the early universe, to get an early picture. But our stars are really just old now, but they preserve that information, or they have preserved this information for a long time. So that brings us to some big questions. Now we know that the out process is operating because we have seen the patterns in the old stars. We have these elements in the periodic table. They have to be created somehow. We understand the slow process. We do not really understand the rapid process. We only know that it works and that it's a universal thing. Time and time again, when we see it, it always looks identical. So the question is, where could it operate? Core collapse supernovae? Well, as I mentioned in passing, when a supernova is sort of building up, a neutron star is formed in the core. Neutron stars means lots of neutrons, which is what you would need to get the out process going. So that's a pretty natural side to think of. Neutron star mergers, well, that's even more neutrons. You have two neutron stars, they orbit, eventually they merge, neutrons galore when they merge. And there are also other options, but I'm not going to talk about those. What's the rate and the yield of the event? These are associated questions, and is the dominant site changing over time? All good questions for which we don't really have answers yet, but we recently got some good clues. Now let me tell you a little bit about supernovae, the pros and cons for hosting the out process. Now, if you found yourself an old star, you can deduce that it must have formed pretty early in the universe, which means every metal you observe in that star must have formed beforehand. And it couldn't have been that much time beforehand because, the star's pretty old. You can't go further back than the Big Bang. And so what you really want is a fast enrichment source. Otherwise you would produce the metals the elements after the star is born, that's not really helping. So supernovae are really good to give you fast enrichment. But the problem is that the theorists for a long time have had problems with the modeling. There seems to be not enough oomph to really get to all the heaviest of the heavy elements. Now what's happening? So this is the proton-neutron star in the center of this emerging supernova, and the shock or the implosion happened. You had the core bounce, and then this material, or this shockwave plows into the surrounding gas. It needs to actually, it stalls a little bit, and it needs to get jump-started from all the neutrons, the neutrinos, from all the neutrinos that come out of the, or a byproduct of the making of this neutron star here. Okay? And so in the wake of these neutrinos, this is the neutrino-driven wind here, these yellow fingers, you can have a process occur. Right? But it just doesn't have enough oomph, as I said, to make it all. So as a consequence, only 10 to the minus 6 solar masses of iron of our process material are produced. And if we translate that into europium, which for a number of reasons is an element favored by observers because it's easy to measure in the spectrum, it's only 10 to the minus 7.5 solar mass of europium per event. That's, even for me, not a lot. Alright, so then neutron star mergers. The pro is that the theorists have no problem producing all the elements all the way up to thorium and uranium in basically the right amounts. That translates into 1,000 times more europium than in the supernova case. But there's a problem, namely that, here's a depiction of the in spiral. It actually takes quite a while, potentially, for these two neutron stars to lose enough energy in spiral and then merge. Okay? And there we have it again. This is not a fast enrichment channel. That had me go around for nearly 10 years telling theorists, go back to the drawing board, and it's like, I have data, you should listen to me. About how it goes in science. Sometimes we were not quite right. And I will tell you in a little while why this isn't such a big problem as we thought it was. It's always good to learn something new. Alright, so here are just some more details on where this happens. So, it's kind of, it starts crushing into each other. And you also have neutrinos coming out on the poles. You can have actually two different types of arc processes in a neutrino, in a neutron star merger. So there's a lot more we have to learn about nucleosynthesis and neutron star mergers, but it's an interesting new game. All right. So now we need to turn to dwarf galaxies. And this is a picture here of the Milky Way. All the little dots depict little dwarf galaxies that have not yet been eaten, or some are quite tightly nudged, so they look like a cigar, because they get shredded in by the tidal forces of the Milky Way sometime soon. And one of them, not quite so nudged yet, is Reticulum 2 there towards the South Pole. And as it turns out, this one is quite an interesting little galaxy. It's actually one of the very faintest ones we know. Has hardly any stars. You can see some stars here. These are all the stars in the direction of the galaxy. The little bars here are just saturation effects, so that's artificial. If you take out all the foreground stars, then you're left with this. I hope you can see something. If you can't see anything, that's cool too, because there's really not much to see. Okay, this galaxy has maybe a few thousand stars, sitting pretty close, so it looks really big on the sky, but it's really, really wimpy. There's really It's hardly a galaxy at all. But it has a dark matter halo, and so that's what makes it a real galaxy by our latest definitions. And there are other reasons why this is an actual galaxy. I'm mostly showing you this for the movie. So we observe, MIT Physics has access to the Magellan telescope in Chile. It's a 6.5 meter telescope in the Atacama Desert, 2,500 meters up in the mountain. It's actually two telescopes, two twin telescopes. This is the one that we're mostly using, the Clay telescope. This is the Milky Way with the Bulge and the galactic center. It's very, very nice and bright in the southern hemisphere because the next door spiral arm is backlit by the bright galactic center until the moon comes up. Occupational hazard. And so we observed the 9 brightest stars, I think, or 7, no, 9, yes, 9 brightest stars in that little galaxy for a few hours each with high resolution spectroscopy to get data. Now we wanted to just take a look because nobody had done this kind of work with that galaxy, but I have done this for a number of ones, so this one was just the next one, on the list. And well, we were surprised what we found. We had certain expectations for what we would find, namely really low abundances of neutron capture elements like europium. That has been seen in all other dwarf galaxies. And so we were just like, oh yeah, okay, let's do the next one and let's see it again, let's have it. Well, what we had was a phone call at 3 in the morning. Anna, I observed the wrong star. And I said, you better not. There is a europium line in the spectrum. Oh, I was like, send me the data at 2 in the morning. That was fun. And so I made a joke. It's like, Alex, my former student, is like, Alex, I think you found the first R-process galaxy. Because we had never found an R-process enhanced star in a small dwarf galaxy, ever. We had no expectation to find one either. And then he found 7. So there's no accident and no wrong observed stars, because these stars are so incredibly rare. You're not just stumbling across one by accident, right? And so you can see here the fat, although ugly, europium lines. This is an R-process Milky Way star, and this is other dwarf galaxy star that is nothing. And here's barium, maybe a little barium, but it's small. And then here's barium also for these stars. So 7 of 9 R-process stars in this galaxy. What's going on? Well, we measured the abundances. It's like, okay, let's put this to the test. Is this really an R-process origin? It is. The purple is the R-process pattern. In gold, you have the S-process pattern. And you can quite clearly see, even in this worst of cases here, where the data was so bad, because these stars are so faint, that you can only get 2 measurements, but it clearly matches the purple pattern and not the gold pattern. So that's pretty easy. All right, cool. How does this compare to the other dwarf galaxies? Again, compared to our expectations. In blue, in color, you have abundances here of barium and europium against iron that again show very low values compared to typical Milky Way stars that you see in gray. So this is what we expected, but this is what we found. The red ones are the Reticulum Stars. But you see here, these 2 guys, they look like the other stars. Those are the ones that did not have these walking lines. So something's going on in this galaxy, producing you normal dwarf galaxy stars and then giving you this bunch of R-process stars. So we were super intrigued and poked around, and we got to ask a few questions. Now, the first question is, how rare is it to find an R-process galaxy? And here's the cool thing now. Previously, we have used individual stars to figure out, okay, well, you know, what is the composition of this early gas from which it formed. And now we're using an entire galaxy for that. Okay? What happened early on in this galaxy? And we had at the time 1 in 10 dwarf galaxies were R% rich. Now it's like 2 out of 15 or so. And we can estimate how many supernovae were, you know, maybe have gone off in this population of 10 dwarf galaxies at early times. And then we get out that 1 neutron star merger occurs perhaps per few thousand supernovae, which is sort of in line with what other people have derived for the neutron star merger rate as well. And LIGO, of course, will give us, hopefully in a few years, some more definite answers. And so this is just like a little fun game to see if that kind of makes sense. But then the question is, how prolific was this event? And this is where the new stuff comes in. For the R% stars in the Milky Way, we don't know their origin. Right? I already said that. And that's a problem. But now, where we have these stars in a dwarf galaxy, we do have information on the origin. Namely, this dwarf galaxy, which means we can place limits on the gas mass into which this R% yield was diluted into. Right? That's the new thing. That was the groundbreaking change here. And 10 to the 5 is sort of the mass of a star-forming cloud, and the mass that's kind of gets swept up by something that has a supernova energy, and a neutron star merger has about a supernova energy, so it's actually not that different. And the maximum mass, very easy, the maximum mass is the entire mass of the galaxy, because it's such a small galaxy. And so we then did a little back of the envelope calculation. So we mixed our neutron star merger yield into 10 to the 6 solar masses of gas, so we just took 10 to the 6 here. And then you can predict what the abundance of europium should be for the stars formed from that gas, which is what we want to compare with what we measured in our stars. And it does agree. So here's the calculation for europium, minus 1.2 plus minus 1 on this logarithmic scale here for the factor of 100 in our uncertainty in the gas mass, so that's the bracket. And it kind of covers the data pretty okay. You can play the same game for barium, gets you this. You know, something sticks out, but this is astronomy, and so it's good enough. We can afford that. Now, this is awesome. We found the first evidence for the existence, although long ago, of a neutron star merger. And at the same time, those actually don't necessarily go together, but at the same time, we also ruled out supernovae, because here's the supernovae, 3 orders of magnitude down. And look, it explains everything else in all these other galaxies. Now, there's no way you can not have supernovae in any dwarf galaxy. You will always have massive stars, and you will always have supernovae. But you may not have a neutron star merger because they're so rare. Okay? But you always have supernovae. And somehow we need to explain these abundances too. So if there's some kind of failed or limited R process operating in supernovae, then it would need to be really low, because it would need to explain all this, you know, these small amounts in the dwarf galaxies. And it does, look. Most of these are upper limits. The errors are upper limits, right? So most of the true data points are probably somewhere down here. So perfectly matches what we see in a normal system that has normal chemical evolution going on, just driven by supernovae. So that was really nice. That brings me to some answers, and I'm going to wrap up. And I need to tell you one more thing about why the time scale for the neutron star mergers actually works as well, and I'll do that before I talk about this. So the cool thing is, first of all, that new calculations for the in-spiral time show that the in-spiral time can be as short as 30 million years, but we assumed 100 million years, so that was on the short end for the earlier calculations. Now, as it turns out, you have a small dwarf galaxy. You can't just inject, so you could be a pundit and say like, well, why don't you just inject 1,000 supernovae into your little system to bring up the abundance to the neutron star merger level, right? Many supernovae, many massive stars out there. But what would happen if you do? You add 1,000 times supernova energy, and this is a small, fragile system, we would blow the whole thing apart. But we know it has survived until today, so there wasn't such a thing, okay? You can rule that out. So that's cool. Coming back to the in-spiral time, 100 million years. Now imagine you have just a few supernovae in the system. That's pretty realistic. And so what would happen when you had some energy injection? The thing puffs up a little bit, but that means it's also hot. So it needs to actually cool down again and clump and fragment to actually form the next generation of stars. And guess how long that might take? About 100 million years. Okay? So while the system is doing this breather from the earliest from the first supernovae, there is time for a neutron star pair to in-spiral and merge. So that's how we solve that timescale problem. By looking at the dynamics of the whole system, something we couldn't do before because we didn't know in what kind of systems the Milky Way are process stars for. All right, I'm way over time, I guess. Answers to the questions? Well, it's probably not core collapse supernovae, although maybe it produces just little amounts in normal circumstances, but nothing like what we've seen in the R process enhanced stars. Most likely it is a neutron star merger, at least it works very well with the abundances collected from Reticulum 2, and as we find more dwarf galaxies and look at them, we will hopefully find more of these guys to play that game again. Other options remain possible, but we'll have to see about that. And the rate is something like 1 per few thousand supernovae, so 1 neutron star merger. And the dominant site is probably not changing over time because we have found evidence for a neutron star merger that happened something like 30 billion years ago. LIGO has found one a year later after we said it should be neutron star mergers. LIGO said that LIGO found something that was very close, very local. So we have at least 12 billion years in between, and so the site probably doesn't change with time, but rather sticks with one thing. All right, so the future is sort of here. We are finding these little dwarf galaxies. LIGO is doing its thing, and certainly on my end, we are using nuclear astrophysics to learn about near-field cosmology and even the formation of the Milky Way, by the way, because of course, dwarf galaxies tell us about how the Milky Way formed. And it's really good fun working on that because it covers so many different topics, right? Nuclear physics, chemical evolution, early galaxy formation, metal mixing processes, how big galaxies form, and so forth. And new dwarf galaxies are actually still being discovered. A new one was announced just a few days ago again. They're so faint and difficult to find that that's still an ongoing process that many astronomers are pursuing. And we could really need a bigger telescope too. Here's an artist's conception of a design for a 25-meter telescope, because all we could do in Reticulum 2 was observe these 9 stars, everything else too faint. But of course it would be much more interesting to observe 50 or 100 stars in this galaxy, not just a handful, to really test how, or to see what this is. And why we have R process stars and there are no non-R process rich stars, so that's another little puzzle that we'd like to tackle, but We might need to wait a few decades. We shall see. All right, very good. So this is my story for today. Now, in shameless self-promotion, and because the holiday season is coming up, I want to do a quick advertisement. So if you like what you heard or like to share it with others, you can watch a mini-series that I made a year and a half ago or so about the formation of the heaviest elements. So you can see it all again. Now, if you like to read, you might like to read my book. A long time ago, I had too much time on my hands before I had children. So I wrote a book. That's what you do. I happen to have 3 in my office. If you'd like to get one, I'm happy to sign it for you. You can also take a look. If I'm out of books, I have a list. You can sign up your name, and I'll get you a signed book that you might either read yourself or give as a present. Yeah. Christmas coming up, or whatever you're celebrating. It explains basically all the early part of my talk again. The Reticulum 2 is not in the book. That came afterwards. But that is the sequel, basically. So now you need to read the prequel. And, and I wanted to show you, because we're celebrating Sagan Day, I actually do have a picture of an apple pie here. The cosmic origin of an apple. Okay, an apple and an apple pie in here. So it's very much in line with today's theme. And of course I am quoting Carl Sagan here and there. And I have my own version of how to explain the existence of an apple pie. So thank you so much for coming and for listening.
Thank you, Dr. Frebel. So would you like to take some questions?
Yeah, sure.
So,
Yep. This one has wheels. Maybe. I better not say. That's okay.
You said
Yes.
that we don't know the origin of our process stars in the Milky Way.
Yes.
Is it possible now that we know that they're in this dwarf galaxy, that they're just simply dwarf galaxies that were swallowed up by the Milky Way and they just happen to be around?
Well, so the our process Milky Way stars probably came from equivalent systems like Reticulum 2 that were absorbed.
Okay.
That's right. But not all dwarf galaxies are created equal. So we can't really make up how massive they were. They could have been as tiny as Reticulum, they could have been bigger. And so that's the problem. We can't really guess that. And so we don't have any tangible information on the environment, only qualitatively.
Thanks for a great talk. And why does the dark matter make it a real galaxy?
So when you have a bunch of stars that are spatially co-located, you have basically 2 options for what it could be. It could be a star cluster or it could be a galaxy. As it turns out, a star cluster is, as the word says, is just a cluster of a bunch of stars. And that one is not embedded in a dark matter halo. Galaxies, however, like the Milky Way has a huge dark matter halo, and all other galaxies have. And as it turns out, there are tiny, tiny little, things that look like star clusters, and they also happen to be embedded in a dark matter halo. So when was it, 2010, I think? There was sort of a new definition adopted for what it actually means to be a galaxy. Because with these wimpy systems, how can you tell? And so one main criterion is that there has to be a dark matter halo that keeps the baryonic, the luminous matter in place.
How do I know it's there?
And so what you do is you measure the velocity dispersion of the stars. Now in a cluster, the stars, in a cluster the stars kind of basically all go around roughly the same way, right? It's a gravitationally bound system. But in a dwarf galaxy, because the stars feel the matter and the dark matter, the stars kind of go more zigzaggy as they go around. So the star clusters have very narrow velocity dispersion, so that most of them have the same velocity going together, kind of like hand in hand. And in the dwarf galaxy, because of they feel much more mass, even though we can't see the mass, they're like all chaotic. It's more like a stampede. And so that gives us an indication that there must be this extra mass out there, which is the dark matter.
But you don't actually know what it is yet, right? Like, I don't know.
Nope. Hey, we have to stay in our job somehow.
Thank you for a great talk. Just briefly, what are some of the possible more exotic candidates for processes that might produce the signature? Like the third option that you said you were going to.
The site. Yeah. So some people put forward the idea that rapidly rotating massive stars could result in some crazy exotic magnetorotationally driven supernovae. So just like really extreme crazy things, and the rotation and everything would like intensify the neutron flux, and that could give it enough oomph to really kind of shoot all the way. Now, I've spoken with some of these authors, and they told me themselves, like, yeah, we just turned the knob, until they couldn't be turned any further to see what would happen, and if that was a possibility if you go to the extreme. And it seems to be a possibility, but nobody knows if that's a physical reality. So that's the biggest challenge, and there are several papers now that said, oh yeah, it could work, and like, oh no, this is overestimated by a factor of 100. On top of that, of course, we have never observed any of these things directly, and we also can only speculate, or hence we can only speculate about the rate. The supernova would make it more frequent, but then, if they don't produce quite as much, but more than a normal supernovae, maybe that could be a welcome middle ground. We don't know. So more work is needed. Again, keeps me in the job just fine.
I have a question.
Oh, sorry.
So recently I got some news that there was a 13.5 billion-year-old star discovered or something like that.
Yeah.
On Hopkins. Was that kind of, has that been looked at all, like analyzed in terms of spectroscopy?
Do you know an author? Or an author on the paper?
No, it's just John Hopkins.
Oh, okay, then I know. Yeah, actually, it happens to be a star that I also work on. Just with all of this and whatnot, paper has been delayed. So what they found was that they had an old star, and it actually happens to have a companion, and the companion is really, really small. It's only 0.15 or so solar masses. So that's hardly a star. Right? A star is defined by having nuclear fusion going on. So if it's not massive enough, again, there's not enough mass sitting on top of the core, which makes it not hot enough to actually, start igniting some hydrogen reactions. And but from the mass and from some other numbers, you can deduce an age, and they deduced an age for that little guy to be 13.5 billion years or so. All of these numbers have huge error bars in astronomy. Okay, 1 billion year, no problem. So I would take that with a grain of salt. However, the primary star that I'm also working on, that is exceptionally metal poor, and so that's exciting in itself. So there's no doubt that this system is very, very old. I'm just always very hesitant to put exact numbers on it because there are so many systematics, and we will never be able to beat them. Again, occupational hazard. It's a different way to confirm, at least roughly speaking, that metal poor stars are old, and so that was a pretty clever way.
And are there any new telescopes that are being planned for this field?
Yeah, this big one I showed the picture of. The problem is they're kind of expensive, and there's kind of not enough money around. So we'll see. The thing is, so right now the biggest telescopes are 6 to 10 meters, and they're pretty fine. But if you wanted to build something bigger, it needs to be much bigger. Right? 12 meters wouldn't really help us. We really need to go much further. And so the next generation telescopes, there are 3 in the planning: one 25 meter, one 30 meter, and one 42, I think. No, 39. It got downgraded. And they cost $1 billion, but in old dollars. So, and then it takes as much money to actually operate them for 10 years. So, if you want to donate $1, that would be appreciated. But it'll take more time, just because this is really a big leap. But that's what we need. And even with those much bigger glasses, it's actually not helping me all that much. It's going to make it better, but it's not going to be, a totally new frontier, at least in my field, this high-resolution spectroscopy. That's just really hard business anyway. So we'll see. We'll hang tight for now.
Why did you say that metal poor stars are usually heavier and bigger? Like, what's the intuition?
They aren't. The first stars were more massive.
And they were metal poor.
Say again?
And they were metal poor.
Well, so the first stars are metal free, actually, in that nomenclature or that jargon term, because it was just hydrogen and helium, and they were really massive because they did not contain any metals. Well, they're formed from gas that did not contain any metals that facilitated enough cooling and fragmentation to make small stars.
Well, there are no more questions. Let's thank Dr. Frebel again. And thank you all for coming. Feel free to have some more whatever's there. And also I put some pale blue dot taffy over there, so please help yourselves. There's a bag there. Yeah, it's right out, the trash is right outside.
Okay.
Thank you all for coming again. And our next event is on December 13th. That's a screening of the film Kumare. It's about a guru who, someone who starts like a fake cult, basically, and it's kind of interesting to look into, how cults form and spirituality and stuff like that. So that's on December 13th evening. The event is already up on our Facebook and other calendars. Yeah, so thank you.
Thanks.